NASA just got $125 million they didn't even ask for. The reason? Nuclear-powered rockets.
In order for a craft to be able to leave Earth's magnetosphere, it will have to have a magnetosphere similar to Earth's to do so. GSI, UCLA, Berkeley, Princeton, Ohio State, every prestigious university on the planet states this as a fact. Every single space-faring nation from NASA and ESA and Roscosmos all agree with this fact, and that is why not a single one of them is willing to spend any money or spend any lives sending them outside of the thermosphere. Since 2014, this information has been available for all of the nations, and they have been working together on trying to figure out how exactly they can push beyond this 230-mile mark that we've all encountered. 6 months ago, we found technologies showing the possibility that if we created miniaturized nuclear reactors, we could create enough power to energize a lithium-ion cell and create enough radiant energy to push off the radiant energies found at about 350 miles in the thermosphere. When this was found out, we immediately started working with other nations on creating satellites like the ICON and various systems that can start measuring the radiant environments of the thermosphere at about 350 miles up. The highest space mission to ever be flown was in 1993 by the space shuttle, and it was at 350 miles up. There was exposure to particles that causes cancer, and these were the reasons why no missions have been flown that high ever since then, and the Hubble has not been serviced. In 2014, Marco Durante showed exactly what happens to the human cell and why no human has been able to go past the thermosphere.
An orbiting field generator placed between Mars and the Sun, like a giant space umbrella. The resources and energy needed to build this is insane.
If we could block the solar wind from stripping away the atmosphere, it might start to build back up again someday. All we would have to do is figure out how to generate the field. Then it would reach out into space and do the rest.
Jim Green.
And if engineers can design a system that generates enough power, we might one day be able to create magnetic force fields around spaceships that direct radiation, just like Earth's magnetic field. Right now, though, we're still looking for the right solution.
An explosion at a remote site. Shifting stories from the Russian government and nuclear officials. Public concern about radiation exposure. We're not talking about Chernobyl 33 years ago. We're talking about 2 Russian military accidents near the Arctic Circle, one just last week.
So how does all of this work? Well, it's actually pretty simple. A miniaturized nuclear reactor is going to be stationed in the back of the craft. The back of the craft will have to have shielding, passive shielding, hydrogen, polymer-based, transitional metals, things that we use on the International Space Station, things that we use within our nuclear reactors here on Earth. They will keep the properties, the radiant elements that are given off by the nuclear reactors to a minimum and keep our astronauts safe. The exterior of the craft, however, will not be conventional titanium or passive transitional metals like used on the International Space Station. The reason why it's going to be lithium is because we are going to use all the radiant energy that we pull from the nuclear reactor, and we are going to put all of that into the lithium cell. The nuclear reactor should be able to create enough energy to push the radiant energy from the thermosphere away from our craft. However, we will be able to use passive and transitional metals to shield ourselves from the lithium metals as well as from the nuclear properties. We'll be able to be shielded from the hull itself that is shielding us from the radiant properties of space. However, will still be shielded from the nuclear reactor that's in the rear. Now, all of this will still be a conventional liquid-propelled rocket like Russia has been working on in the past couple of months, while we just saw that nuclear reactor melt down on one of the liquid hydrogen rockets just a few months ago. These are things that they're working on in hopes that eventually they're going to be able to create this technology. And then, since Russia and China have signed the new space treaty and they are building a space station at 230 miles up by themselves, we are not allowed. We have started Space Command and we have activated a new Space Force, and now we are going to make the Artemis mission and the Gateway, which is our new Skylab, and we're going to put it at 350 miles up. If we can figure out how to push off the radiant environment, or if we can create a better system like they just sent up onto the International Space Station this last week with the vests that will assist in blocking some of the heavy cosmic rays. So it's all very straightforward. The nuclear reactor in the rear will be shielded by passive and transitional metals. It will be powering the non-conventional lithium hull that will push enough radiant energy against the radiant energy in space and keeping the astronauts safe. That is going to be powered by a conventional liquid propulsion rocket, and this is a technology that they're currently in the works of making. That's why you just saw the nuclear reactor melt down over in Russia. However, it was on a liquid hydrogen rocket, but it wasn't meant for warfare. It's because they're working on this technology in hopes that they can get 350 miles up, because we've only ever made it to 230 miles up. That is why the last Apollo mission, Apollo 18, Apollo-Soyuz, was to 230 miles up to rendezvous, where we've been ever since. It's that simple, guys. This is the next step, and we cannot leave the thermosphere until we have it, and even if we do create it right now, it's just going to bring us into the next layers of the thermosphere. 350 miles up, still 6,000 miles below where the atmospheric layers end.